I'm still debating whether or not I should try to prove something hard today. You know, it's like, I don't know. Let's see, I think I forgot to hand this out last time, so you guys can do 2 days. If you can remember whether you're not here Friday, so you can check it or not as appropriate. But anyway, I will begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for the students, just class. Just ask you to be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. So I gave you guys, I hope, some like decent, somewhat non-trivial examples of how to find a basis for a subspace, right? And of course, if we can find a basis, which is an ordered set, which is both linearly independent and spanning, then we can write down the coordinate map. So let me do just a couple more examples of that nature. And I want to introduce some new subspaces. So that's kind of more broadly what I'm after today. But first, let me just wrap up a couple things about coordinates. So bases for matrix spaces are kind of, that's a special topic. There are really 3 kind of ones that come to mind immediately. Number 1, we can talk about column space of a matrix, right? Number 2, we could talk about row space of a matrix. And number 3, we can talk about the null space of a matrix, right? So here I have A is a m by n matrix over some field, all right? And so the definition of column space, of course, is it's just the span of the columns, right? How many columns? I guess there are n of them, right? And the row space is also, by definition, the span of the rows. There are m of these. M as in mommy, right? And the null space, well, this is not defined by a span, but it's defined by an equation, right? So this is x in Fn such that Ax equals to 0, right? Now, we proved the other day that the null space is a subspace by the subspace test. It was like so much work, right? We had to do all the work of picking x and y in here and showing that A times cx plus y is c times 0 plus 0, which is 0. Therefore, cx plus y is in the null space. And since 0 is in the null space, it passes the subspace test, right? It's easy to prove that the null space is a subspace by the subspace test. And since we have the span theorem, the fact that the column space and the row space are subspaces is also like no work at all, right? It's just manifestly clear by the span theorem that this is a subspace of what and this is a subspace of what. The column space is a subspace of Fm, right? Because every column is formed with m rows, which makes it an m vector. The null space is a subspace of Fn, all right? And the row space, well, that's a subspace of F, 1 row by n columns, all right? So these are the fundamental subspaces that we attach to a matrix, all right? And there is a standard technique for finding the basis for each one of these. Like, how do you, I don't even want to write it down, I just want to talk about it with you guys. How do we find the basis for the column space? We use what? Oh noes. Well, how do we find the basis for the column space? How do you form the basis for the column space? What gives you a linearly independent set of columns which span the whole column space? Row reduction. Yeah, but which columns? The pivot columns, right. We can build any non-pivotal column with the pivot columns. And this is, we have the column correspondence property, which I think I talked about here the other day, right? So by the column correspondence property, any linear dependence amongst the columns of A can be seen in any row equivalent matrix to A. The most easy of those to look at, of course, is the row reduced echelon form of A, from which we can manifestly read off any kind of linear dependence that there may be between the the pivot and non-pivot columns, right? So like, for example, if A, had the reduced row echelon form of A having the form 1, 2, 0, 0, 0, 0, 0, 0, 1, 0, 0, 3, 4, 0, 0, right? If that's the case, then the column space of A is the span of what? It's the span of columns 1 and columns 3, right? Because you can see that column 2 is twice column 1, and you can see that column 4 is 3 times column 1 plus 4 times column 3 by the column correspondence property. I don't even need to tell you what the form of A is. This is going to be the case, okay? Now, how about the null space for this matrix? What's the null space of A look like for my example 1? Basis for the null space, how do we do that? Can I find the basis for the null space without actually knowing the matrix itself? I mean, I can't make explicit the column space without actually knowing the first and the third columns of this matrix, right? But I would point out to you that actually, yes, we can explicitly find the null space here despite the fact that we're ignorant of the actual form of the matrix, except that it has that row reduction, which is kind of neat if you think about it. All right, so the way we find the basis for the null space, I'll remind you, we look at AX equals to 0, right? And we just work out what that means. So here, X is equal to X1, X2, X3, X4. And so my row reduced matrix up there, it reveals for me X1 be equal to minus 2x2 minus 3x4. And, well, x2 is x2, x3 is minus 4x4, x4 is x4. Anyway, so x is equal to, apparently, x2 times minus 1, 1, 0, 0, plus x4 times minus 3, 0, minus a 4, 1, like that. And so my null space is the span of minus 1, 1, 0, 0, and minus 3, 0, minus 4, 1, if I haven't made a mistake. So the point is we have to write down the solution to the homogeneous equation, factor out the parameters, and the vectors which remain form the basis for the null space. This is not an accident that the null space is two-dimensional, the column space is two-dimensional, right? Because remember, we have the rank nullity theorem. The dimension of the null space plus the dimension of the column space has to be equal to the number of columns in the matrix, which in this case is 4. Right? Now, I don't talk much in 221 personally about the row space, but the row space has a basis which is given by the non-zero rows in the reduced row echelon form of A. And if you want to use the rows of the original matrix for a basis, then the trick you can do is take the transpose of the matrix, row reduce that thing, then the pivot columns of the transpose will correspond to the original rows of the matrix, which serve as a basis for the row space, if you were so inclined. This is all written in detail in the notes, but yeah. Okay, so there you go. Let's go on. So I want to talk about subspaces today. And so like there are some very important examples of subspaces that we should know about. And I haven't looked at your mission 2. Like I wrote your mission 2 a while ago, you know? I should take another glance at it. I don't want to inadvertently do your homework. You know? You don't want that, right? Let's see here. Yeah, I don't see that. Okay. Okay, good news. I can prove the theorem today. All right, good. So like, I have deliberately not put certain proofs in the notes because I want to reserve those for homework, but maybe they're not homework for your class. But they're good homework to do. So, given V over F, a vector space, right? You notice that we have 0 is a subspace of V, and the whole space is a subspace of V, right? So the trivial subspace and the whole vector space are themselves subspaces. Those are examples we should keep in mind, all right? However, if W is a subspace of V and W is not equal to the 0, or if it's not equal to 0, then what? W is non-trivial, a non-trivial subspace, all right? This is a little language we should make sure we're on the same page about. If W is a subspace of V and W is not equal to V, then W is a proper subspace. All right, so I sometimes use those terms without thinking, but that's what they mean, okay? All right, so theorem, proposition, whatever you want to call it, theorem, given U a subspace of V and W a subspace of V, we have, number one, we can show that the intersection of U and W is a subspace of V. All right? So the intersection of two subspaces is a subspace. And number two, if we say U plus W, here's what this is going to mean. X plus Y, such that X is an element of U and Y is an element of W. All right? Guess what? This is called the sum of the subspaces. Guess what? The sum of two subspaces is, again, you guessed it, subspace. All right. Okay. So I threatened to do homework on these, but since I haven't, I kind of owe you the proofs in here, all right? I always tell the story. Once upon a time, there was a linear algebra class where on the final exam, not a one of them could prove that the intersection of two subspaces was a subspace. For that reason, I awarded no one an A, because I could not in good conscience give an A to anyone in a class where no one could prove the intersection of two subspaces is a subspace. Because everyone should be able to do this problem. It's so easy. Check it out. It had been in their homework in previous tests and things. It's not like they saw it for the first time on the final, all right? Anyway, so here's the proof. We use the subspace test, all right? So first of all, observe for one. Note, 0 is an element of U, and 0 is an element of W. Hence, 0 is an element of U intersect W. You guys remember intersection. I don't need to redefine I'm not going to define intersection here. You guys know what intersection is. We're not going down that path. So it has to be in both. So 0 is an element of there, which means that what? This is non-empty, right? So that's step number one. Note, U intersect W, a subset of V, is clear. That's so clear that if you didn't write this sentence, I wouldn't take points off. All right, I myself forget that half the time. So it's bad form for me to take points off for something I always forget, right? Let X and Y be elements of U intersect W, and let C be a number in the field. Notice like number 1, Cx plus y is an element of U since U is a subspace of V. Right? Because a subspace is closed under scalar multiplication and addition. If you'd like, I could state these separately. Like, let me do that. So, sorry, I'm getting too sloppy here. Cx and x plus y, right? This and that are elements of U because U is a subspace, right? It has to be closed under scalar multiplication and addition by definition of subspace. Number 2, Cx and x plus y are elements of W, since W is a subspace of V. What does this tell us? Therefore, Cx and x plus y are elements of U intersect W. Hence, by subspace test, U intersect W is a subspace of V. And there you go. That's all there is to it. So if I put this on the final, you guys are going to get this one, right? Not everybody has to get it. Just one person has to get it to preserve the A. You know, I feel like I owe the other class to give everyone a B. I am honor bound by whatever my syllabus says, right? Like, I can't rewrite the syllabus to take away your points. You know, that's not within my powers. As far as I know. I wouldn't do that. Okay, so anyway, any questions? So how about the number 2? Can we prove that the sum of subspaces is a subspace? How's that going to go? How about 0? Is 0 in there? Well, 0 is in both subspaces, right? What's 0 plus 0? 0, right. Note, 0 is an element of U. 0 is an element of W. And 0 plus 0 is equal to 0. Thus, 0 is an element of U plus W. We have to interact with the definition of the sum. The definition of the sum is that it's formed by elements that are sums of the subspace elements, right? Okay, so then what? Suppose that let me use A and B are elements. Let me not use that notation. I'm sorry. I'll get it eventually here. Suppose that Z1 and Z2 are elements of U plus W, and C is in the field. Then, by definition of the sum of U and W, there exist what? X1 and X2 in U, and Y1 and Y2 in W, such that Z1 is X1 plus Y1, and Z2 is equal to X2 plus Y2. Right? That's the definition of the sum of subspaces, that an element, an arbitrary element in the sum can be written as a sum of elements in the subspaces being added. All right. So what do we want to do? Let's notice that x1 plus x2 and also cx1 are elements of U, since U is a subspace of V, right? Likewise, y1 plus y2 as well as c times y1 are elements of W, which is a subspace of, well, since W is a subspace of V, right? I know that the linear combination of X, I mean, the addition of X's, the addition of the Y's are again respectively in the U and the W because we're assuming they're subspaces, right? Then what? Well, then if we look at Z1 plus Z2, what do we got? This is X1 plus Y1 plus X2 plus Y2, right? But, aha! Oh, hey, hold on a second. Oh, actually, it's up on my desk.
What is?
The other remaining homework.
Oh.
So.
Okay. Should I go get it?
That'd be good. You can wait till, like, I mean, whatever. If you can find it, you can find it. If you can't, I mean, it's well, anyway. If you wait, I'll try to, if you're around later, I'll give it to you, but.
I'll be somewhere, I guess.
All right, well.
Maybe I'll come tomorrow morning.
Okay. But then vector addition is commutative and associative, right? So we can rewrite this as what? Like x1 plus x2 plus y1 plus y2, which is what? An element of U and an element of W. So this is manifestly an element of what? U plus W, right? So that shows we have closure under addition for the subspace. What's next? How about scalar multiplication? How about C times Z1? Well, that's C times x1 plus y1 by our previous comments, which is CX1 plus CY1 by, like the defining axioms of a vector space. That's how scalar multiplication works. But we just had up here that CX1 is in U and CY1 is in W. Consequently, this is an element of U plus W, right? Thus, U plus W is a subspace of V by subspace test. And we're done. What do you think? I think, personally, I think these proofs are they're pretty relaxing, actually. These aren't bad, right? Not bad at all. It's actually a much more annoying problem to actually have to find the basis for one of these things. Like, how do you actually find the basis for the intersection of two subspaces? For a given example, like what's the calculational technique? How do you do it? All right. So I have some thoughts on those calculations we'll get to. I'll try to share some of my tricks with you, our techniques. So the other theorem we have, 2.74, it says the following: let V be any finite dimensional vector space over F, all right, with subspace W. Then the dimension of W is less than or equal to the dimension of V, where dimension of V equals to the dimension of W if and only if what? No, I'm saying the dimension of V is equal to the dimension W if and only if what?
The cardinality of the basis is equal.
Well, that's what that means. But here we're in a finite context, so this literally number of things in this basis is number of things in that basis. So what I'm fishing for here is simply V equals to W. If you have a subspace which has the same dimension as your vector space, it's the whole vector space, right? So the proof for this theorem basically rests on the more, the deeper like theorems that we talked about the other day in terms of basis extension. So I think it's good for me just to like apply those here so you can see how it works. So, all right. So we know that V is equal to the span of beta, right? Where beta is something like V1 through Vn, right? And by definition, what's the dimension of V in this context? Just n, right? This is assumed. It's a finite dimensional vector space. I'm just making an explicit notation for the basis for the sake of this discussion to try to make it like as concrete as possible, all right? You probably could get away with not even writing this down and just using words, right? It's possible. Suppose W is a subspace of V, all right? Then W is a vector space. And what does that mean? We had a theorem last class that any vector space has a basis. So that means that, hence, there exists, let's say, gamma, a subset of W, which is, by the way, a subset of V, right? Such that gamma is linearly independent. And what's the other thing? The span of gamma has to be what? All of W, right? So why do you think, why should it be the case that the dimension, what does it mean to say the dimension of W is less than the dimension of V? That, specifically about the things on the board I have. You said it a second ago, it's the cardinality, right? So like the number of things in gamma, we'd like to argue that the number of things in the basis for W has to be less than or equal to the number of things in the basis for V, right? The question is why? Right? So I have departed from the proof. I'm now entered thinking mode, to be clear, right? This is not, like, we shouldn't, it's not good form to write down the thing you're trying to prove, and then, that's why you absolutely must have this y over here, otherwise I would definitely take points off, yeah. Anyway, but why is that true? Yep.
Because W is equal to the span of gamma, and V is equal to the span of beta.
Okay, but why does that imply the number of things in the gamma has to be less than the number of things in the beta? That's where you're stuck, yeah. I mean, how about this? What if we assume otherwise? Like, what would that mean? Like, towards a contradiction, right? Like, suppose the number of things in gamma is greater than the number of things in beta, right? Then, there exists, let's say W in gamma I'm trying to think of how to say this. I should be able to get a contradiction of linear independence of beta from this. Right? Because if the number of things in gamma is greater than the number of things in beta, then what this means then is I have a set gamma which is linearly independent in V with more vectors than the basis. Right? But the basis is assumed to be a what? A linearly independent spanning set. So I think we ought to be able to argue like that. Well, I think we have to use like the replacement lemma that I was talking about the other day. Something like that. Like, since, yeah, I guess, so I imagine starting with, beta is a set of linearly independent vectors, right? And, well, anyway, let me cease this. This is, I'm kind of spinning my wheels at the moment. But I'm pretty sure we can argue that, which implies beta is linearly dependent. Not that beta's. I think that must mean that. All right, have a set with more vectors than beta. So, it must be that there's a vector in gamma which is not in the span of beta, if this is true. And because of that, if there's a vector in gamma which is not in the span of beta, that means if I take beta and union with that extra vector, then I have a linearly independent set. Because if we take something that's linearly independent, if we take something union with it with something that's outside the span, that's another linearly independent set. Which would then mean that we had a set. We had a linearly independent set which is larger than beta in terms of the number of things in it and still span the whole space. But that would contradict the uniqueness of dimension theorem we proved last time. So the argument has to be something like this, but I think so. Unfortunately, this is an example of like, to give a careful proof here, we'd actually have to like get back into the details of what I did the other day and like actually sort of mull over it and be more careful there. And so yeah. So I think we'll have to be content to just say, which implies a contradiction. All right, so we'll take, let's just take as a corollary to yesterday, as something for our future use, okay? Just so you guys have something like concrete to hang your hat on. If the dimension of V is equal to n, then any set with more than n vectors is linearly dependent. All right. That's the heart of what I'm trying to argue. If we have more than n vectors in an n-dimensional space, it must be a linearly dependent set. If it was linearly independent, right, then, yeah, okay. We can prove that corollary if you want. I think I know the proof now. I'm sorry, guys. Best case scenario, I'm just teaching this class, and I have more time to think. But sometimes the day catches up with me, and this is one of those cases. But Do you want me to go through I can go through the proof of the corollary. I think I can say it now, but actually let me just stick with this theorem for a second here. So we have a subspace. So then what's the answer to this? Because if the number is not less than, it violates the corollary. You can't have a linearly independent subset of the vector space which has more than the dimension number of vectors, all right? That's just impossible. I will prove that corollary, the standalone proof next, okay? But let's finish this thought. So what does that mean then? So, okay, well that's it. I mean, since number of gamma greater than number beta is impossible by corollary, and that's a corollary to a theorem that I didn't prove the other class, okay? Ultimately. That implies we're stuck with the alternative, right? Which is that the number of gamma is less than or equal to the number of beta. But this is exactly what we mean by the dimension of W is less than or equal to the dimension of V, right? So that's the first half of this theorem. How about the equality? If the number of things in gamma is equal to the number of things in beta, then notice that the span of gamma is a subspace of W, right? Which is, by the way, a subspace of V. More to the point, gamma is a subset of V, right? Which is with number of beta vectors, right? We could say n. And thus, the span of gamma has to be what? I argued that has to be V. What happens if it's not V? So like if span gamma is not equal to V, then there exists x naught in V, x naught not in the span of gamma, right? Which implies that gamma union to x naught linearly independent. And that's a problem because in this context, that's a set with more than n vectors, which is linearly independent in an n-dimensional vector space, which is forbidden. Because we can't, we can't have more than n linearly independent vectors in a n-dimensional vector space. So that forces the span of gamma to be V, because to say otherwise is to violate the dimension theorem that we proved last time. So this blue contradiction is why this is the case, okay? Which is the conclusion of the theorem. Let's see if I can prove the corollary in a more convincing way. Although I have this feeling I should probably do the subspace calculations. That'd probably be better for you guys. Rats. All right, let's do the subspace. I'm gonna let this sit and think about it, and I'll try to either post a little video with the proof of this, or we'll come back to it next class. Whatever makes more sense. All right. So example. 2? Oh, thank you. Example 2. What if you wanted to find a basis for, how do you understand like intersections and sums and things, right? So like calculationally, let's look at an example. So like W1 equal to, let's say, A in R2 by 2, such that A transpose equals to A. And we'll look at W2 equal to A in R2 by 2, such that the trace of A is equal to 0. Now, it turns out we can prove that both of these are, in fact, subspaces. All right? My question then is, like, what's the basis for the intersection? Okay, so find basis. So what I would do in this kind of context is pretty simple, like W1 intersect W2. So if I have A, which is A, B, C, D, right? In W1, W2, W1 intersect W2, what does that mean? That means we have, A transpose equals to A, and we also have that the trace of A is 0, right? That's what that means. Both of those conditions hold on the matrix. So on the one hand, we have A, C, B, D, like that. So if the diagonal stays the same, flip the off diagonals, right? So there's your A transpose equals to A, which tells us what? Tells us nothing about A. It tells us nothing about D, right? What does this tell us, though? Really just one thing, right? B and C are equal, right? So B equals to C. So we got that, right? And on the flip side, trace of A is A plus D. Well, that's equal to 0. So therefore, apparently, A is like equal to minus D, right? So my matrix has the following form, minus D, C, C, D, which we could rewrite as like C times 0, 1, 1, 0 plus D times minus 1, 0, 1. And so, my basis for W1 intersect W2 in this case would be, well, apparently two things, right? So it's a two-dimensional intersection, isn't it? As it happens. What's the basis for W2, right? If I just have A equals to, A, B, C, D in W2, we get what? A plus D equals to 0, and that's it, right? So we get like A is A, B, C, minus A, right? So my basis for W2 alone, I could write as 1, 0, 0, minus 1, and then like 0, 1, 0, 0, and 0, 0, 1, 0 if you like. So there's a basis for W2. What's the basis for W1 here? That's something like A, B, B, D, right? That's what that looks like. So your basis for those, you could use 1, 0, 0, 0, 0, 0, 1, 0. Oh, my bad. One's here. 0, 1, 1, 0, right? So those, there's the basis for W2, there's the basis for W1. How big is, yes, sir.
So when we're finding basis for something that's not just like R2 or R3, and it's R2 by 2, or God forbid, R2 by 2 by 2, how many...
R2 by 2 by 2, we don't do that. Okay, anyway, go on, yeah.
How many elements are going to be in a basis?
Oh, that depends on the example.
So it could be anything.
I mean, up to, well, there are limits, because if we're talking about a subspace of the 2 by 2 matrix, right? If we're talking about a 2 by 2 matrix subspace, right? Then we have the dimension of the 0 space less than or equal to the dimension of our hypothetical subspace we're talking about here, less than or equal to the dimension of our 2 by 2, yeah? But this is 4. This is 0 because the basis is the empty set. And so your choices are from 0 to 4.
Okay.
Our W1 and W2 in this example happen to be 3-dimensional.
Okay. That makes sense.
Yeah. There's a theorem that I was almost thinking about proving today, but I had the good sense not to. It says that the dimension of W1 plus W2 is actually equal to the dimension of W1 plus the dimension of W2 minus the dimension of the intersection of W1 and W2. Did that theorem work out here? I guess it's hard to say unless we actually calculate W1 plus W2. What do you think? What is, well, I mean, what goes on here? The dimension of W1 apparently is, what do we got? 3 plus 3, right? I'm arguing 3, 3. We work this out, 2. So if you believe my calculations on this board, we've got 3 plus 3 minus 2, also known as 4. So if you believe the other theorem that I almost proved today, all right, what does this say about W1 plus W2? What is it? Allegedly, it's a dimension 4 subspace of our 2 by 2. There's only one of those. It's the whole space. It must be that W1 plus W2 is actually the whole R 2 by 2. Okay, so like this actually example was pretty easy for intersection. The reason for that being both of these subspaces were defined by equations. So when we're faced with two subspaces defined by equations, we simply impose both equations for the intersection. All right. The thing that gets this to be a little bit like fussier is if you're up against something where you've got one subspace defined by an by an equation, but maybe the other one's defined by a span. Let me show you what I mean specifically, just to give you a sense of what you might be up against. Suppose we're in like context example 3. Your vector space might be, say, second order polynomials over the reals, right? And W1 might be the span of 1 and x, all right? And W2 might be like f of x such that, you know, f prime of 0 plus f of 0 is 0. So then, like, how would you deal with an example like that where you're trying to find like the basis for W1 intersect W2? What do you do? So what I would suggest is you, I mean, this part's nice, that's an equation, right? But my real question is, can you rewrite this as like a plus bx plus cx squared, let's say, such that some equation or equations hold? Can you rewrite it as, yeah?
X plus 1.
Well, no, I mean, in W1, a typical thing has the form C1 plus C2x, right? As you look at this equation, what can you tell me about C? Yeah, how about this? Actually, this equation defines the span in this context. The way I saw that was I looked at an arbitrary element of the span equal to an arbitrary element of the space, and then I found conditions, equations, which make this happen from that. So that's my way, personally, of converting a span to an equation. So then if I wanted to, this would be what? Like, in this notation here, that'd be like, B, right, plus A equals to 0. So if I had, f of x is a plus bx plus cx squared, an element of W1 intersect W2 here, that would tell me that two things are going on. A plus b is equal to 0, and also c is equal to 0. So therefore, a is equal to minus b, which implies that W1 intersect W2 is, in fact, the span of what? 1 minus x, I think. I would have had a hard time figuring that out if I hadn't been able to convert both of the subspaces to equations. See, combining equations is easy. Combining spans, you can do if the vectors are sufficiently simple to reason through it, but it's tough in general, I think. But so the c is 0, and a is equal to minus b. Yeah. Oh, yeah, I'm done. Thank you. Thank you.